For most of human history, the physical world was a series of terrifying mysteries. Lightning strikes and earthquakes weren't seen as atmospheric or geological events, but as the direct, emotional punishments of the gods. But in the 6th century BCE, a group of thinkers in the Greek colonies of Ionia began to break this cycle. Led by Thales of Miletus, they started looking for non-supernatural causes for the phenomena they observed. This represented the formal beginning of natural philosophy, the move from mythos, or mythology, to logos, or reason. It was an attempt to provide a unified, rational account of how the universe actually worked. The adoption of this logic spread rapidly. The Pythagoreans applied it to the secrets of mathematics. Democritus used it to theorize the existence of indivisible atoms, and Hippocrates transformed medicine by logging physical symptoms rather than divine omens. By seeking causes within the physical world itself, these early philosophers invented the concept of nature, a system that operates independently of divine whim. For the first time, the universe was something that could be systematically studied. No one pushed this project further than Aristotle. He became the father of systematic observation, categorizing over 500 animal species to prove that genuine knowledge must be grounded in what we can see. Aristotle's greatest tool was formal logic, which he used to build a teleological framework. In his view, every object in the cosmos acted according to an inherent purpose, or final cause. The sun went around the Earth because it was the sun's nature to do so. Using geometry, scholars built this geocentric model, where the Earth sat motionless at the center of perfect concentric spheres. However, this had a fatal weakness. Relying purely on logical elegance, the Greeks rarely subjected their theories to rigorous physical experimentation. This system was so internally consistent that scholars spent the next 15 centuries trying to fit new observations into Aristotle's logic, rather than questioning the logic itself. By the time of the Middle Ages, this physically incorrect model had become the unshakable foundation for all Western education. As the centers of learning shifted during the Middle Ages, Islamic scholars took up the mantle of natural philosophy. They translated ancient Greek and Roman texts into Arabic, using them as a springboard for their own critiques and discoveries. In mathematics, Al-Khwarizmi developed algebra. This breakthrough untethered calculations from literal geometric shapes, allowing for the complex abstract math that would eventually drive modern physics. In the fields of chemistry and medicine, scholars like Al-Razi and Avicenna moved beyond theory. They refined processes like distillation and wrote encyclopedic medical texts that remained the global standard for centuries. By the 10th century, natural philosophy had moved from the realm of abstract debate into a highly practical, applied discipline designed to solve real-world problems. The most significant breakthrough occurred in the 11th century with the physicist Ibn al-Haytham. He looked at the Greek theory of vision, the idea that the eye emits rays to see, and found it mathematically and physically lacking. As seen in this manuscript, he proved the intromission theory, that light reflects off objects and enters the eye, using geometric proofs. He insisted that hypotheses are worthless unless verified through controlled mathematical experiments. This was the birth of the experimental scientific method. Later Islamic astronomers applied this new empirical rigor to the heavens. Using highly precise astrolabes like this one, they measured planetary movements and began revealing the massive mathematical errors in Ptolemy's ancient geocentric model. By forcing mathematical logic to answer to physical evidence, these scholars created the weapon that would eventually dismantle the Aristotelian universe. In the 16th century, refined data and translated logic from the Islamic world flooded into Europe, setting the stage for the scientific revolution. In 1543, Nicolaus Copernicus proposed a universe with the sun at its center. This model challenged centuries of Aristotelian physics, but it finally resolved the chaotic mathematical errors that had plagued astronomers for generations. Soon, Tycho Brahe's meticulous tracking of comets and supernovas provided physical proof that the heavens were volatile and changing, directly contradicting the Greek idea of a perfect, unchanging cosmos. Finally, Galileo Galilei used a high-tech instrument, the telescope, to make the irrefutable observations that assassinated the old model. He saw moons orbiting Jupiter, proving that not everything in the universe revolved around the Earth. Because of these men, direct empirical observation replaced ancient authority as the final arbiter of truth. This new era was formalized by Francis Bacon, who championed knowledge through sensory evidence, and René Descartes, who emphasized the power of mathematical reasoning. The ultimate synthesis came with Isaac Newton. He combined Greek logic, Islamic experimental math, and the new European observational data into a single, unified system. This visualization shows Newton's core proof that the same physical forces pulling an apple to the ground on Earth are responsible for guiding the planets through the sky. Through Newton's laws, the universe was no longer seen as a realm of divine whims. It was understood as a breathtaking, mathematically predictable machine. The legacy of these thinkers is a rigorous methodology, a continuous relay race of human reason, experimentation, and mathematics. For centuries, the most influential thinkers on Earth believed the universe was solved. They viewed the cosmos as a massive, perfectly synchronized brass clockwork mechanism. The laws of motion were so reliable that if you knew the position of every gear, the future was entirely predictable. But that mechanical model failed to account for the living world. The rigid physics of the era couldn't explain the messy, chaotic diversity of life. Why certain species adapted while others vanished into the fossil record. That illusion of a static, finished creation began to fracture in 1859, when Charles Darwin published On the Origin of Species. Darwin proposed that life is a dynamic, mutating process. He observed that offspring differ slightly from their parents, and over vast stretches of time, environmental pressures select the traits best suited for survival. This theory provided a naturalistic explanation for the complexity of life. It unified the biological sciences while forcing a difficult realization. The world was not a rigid machine, but a fluid and evolving system. While biology was becoming more dynamic, the solid gears of physics were also starting to dissolve. In the early 19th century, Michael Faraday challenged the idea that electricity and magnetism were simply physical fluids flowing through matter. Faraday visualized invisible lines of force. He saw a universe where magnets and electrical currents were connected across seemingly empty space by threads of tension. Faraday had the physical intuition, but he lacked the math. That work fell to James Clerk Maxwell, who translated these invisible visions into a rigorous mathematical framework. Maxwell's 4 equations proved that electricity, magnetism, and light are part of the same phenomenon. He revealed that light travels as an electromagnetic wave, moving at a constant speed through the vacuum of space. This synthesis shifted the focus of physics. Instead of measuring the collisions of solid parts, scientists began studying invisible, interacting fields that permeate the entire universe. The demolition of the old order accelerated in 1915. Albert Einstein's general theory of relativity proved that space and time are not absolute containers. They are a fabric warped and bent by the presence of mass. At the same time, the subatomic scale was proving even more chaotic. Max Planck and Niels Bohr discovered that energy does not flow in a smooth stream, but moves in unpredictable, discrete packets called quanta. In 1927, Werner Heisenberg introduced a principle that eliminated the possibility of precise prediction at the atomic level. Heisenberg showed that it is impossible to measure both the exact location and the exact velocity of a particle simultaneously. The more you know about where a particle is, the less you know about where it's going. Einstein was famously repulsed by this, insisting that God does not play dice with the universe. Yet the experimental reality of wave-particle duality consistently supported Heisenberg's math. The mechanical certainty of the previous century was gone. At the most fundamental level, the universe is governed by probability and chance. While physics grappled with uncertainty, biology faced its own missing link. Darwin had explained that evolution happened, but the physical mechanism that stored and passed on those changes remained a mystery for nearly a century. Solving the puzzle required looking at life through the lens of physics. Rosalind Franklin used X-ray diffraction to capture the high-resolution architecture of genetic material, revealing its hidden symmetry. In 1953, James Watson and Francis Crick utilized Franklin's diffraction patterns to successfully deduce the physical structure of DNA. This is a ball-and-stick model of the double helix. Its elegant twisting ladder showed how biological information is encoded in chemical base pairs and how those strands can unzip to copy the instructions for the next generation. This discovery transformed biology into an information science. The mechanism of heredity was no longer a philosophical question. It was a matter of chemical sequencing. The shattered paradigms of the 19th and 20th centuries created the modern world. Every transistor in your computer and every breakthrough in modern medicine relies on the field theory and molecular biology established during this era. This biological revolution reached a milestone in 2003 with the completion of the Human Genome Project. Scientists mapped all 3.2 billion chemical letters that define the human genetic code. From this foundation, we have confirmed the existence of the Higgs boson, detected the ripples of gravitational waves, and developed technologies to reprogram adult cells into stem cells. These discoveries have been deeply humbling. We traded the comfort of a predictable, mechanical universe for a reality that is far more complex and difficult to visualize. We now live in a universe defined by interconnection and probability. It is a world that is far stranger than common sense suggests,